class. This is Summer 2020 Summer School. This is Lesson 1 on electrostatics.
Welcome to Electrostatics. Have you ever wondered why sliding on plastic playground equipment gave you a new hip hairstyle? Or why touching a doorknob after shuffling across carpet produced miniature lightning that shoots from your fingertips? What causes an object like your hair to become charged and to hold on to that charge? And what causes your hair to suddenly release that charge? Let's take a look at what's happening with electrostatics and see if we can answer the question, how do electric charges behave? To address your lesson question, we will identify how electric charges behave, analyze the relationship between electric charges and force fields, identify conductive and insulative materials, and examine how we put charge onto materials. Next, let's look at the vocabulary words that will be used in this lesson. Take a moment to type these 4 important vocabulary words into your eNotes and check your glossary for definitions. Stay on the lookout for these vocabulary words as you move through the lesson. Your science words are Coulomb, electric field, electric force, and field lines. So what happens when 2 objects with like charges are brought near each other? When 2 objects, both with positive charges, are close to each other, they repel or push away from one another. When 2 objects, both with negative charges, are close to each other, they repel each other as well. So the rule about like charges is that they always repel each other. But what happens when 2 charged objects with different charges are brought close together? When objects with opposite charges are near each other, they attract or are pulled closer together. So the rule about unlike charges is that they always attract each other.
Okay, so a quick comment about that is that when she says charges, we're really talking about parts of the atom, and specifically the electron would be the negative charge and the proton would be the positive charge. Generally speaking, it is electrons that do the moving, but you'll see in a way that protons also can effectively move through a circuit. Also, the term like simply means the same, and of course different is different. All right, so the third panel in this introduction is simply asking a question. The glass is attracting the pieces of paper. What does this tell you about the charges on the glass and on the paper? And it just simply says the glass and the paper have different charges as the correct answer. It doesn't tell you which one is positive and which one is negative at this point, but it's just that they have to have different charges if they are attracting. All right, so one of the things I'm going to be doing is walking you through the guided notes. In addition, I'm going to be adding some of my own notes as well, showing you some things you might want to put on in your spiral-bound notebook. And you should absolutely have a spiral-bound notebook. Don't use eNotes. I don't recommend that at all. All you can do is type text. So I'm going to go ahead and do this. I am going to do it live on a dot cam on my desk. That will affect the sound quality a little bit. But I'm going to go ahead and write these on my desk using a dot cam and then add my own notes as I think that they're helpful. With the guided notes is you should have a Kami extension, or you can download it onto your school computer. It's this K up here in the corner. And if I go ahead and click on that, it allows you to type text on the guided notes. I already have this one in my system, but it will bring up some of these utilities on the side. So if I want to type in the answers, I can use a text box. Come on over. I'll go ahead and fill in these first 2. And the first one is analyze the relationship between electric and that word would be charge. And I can click off. And electric force, distinguish between conductors and insulators, and examine charging by, and there's three methods to charging. The second one is conduction. And the third one is induction. So that's one way you can do these. The other way you could simply do them if you want all of your notes in the same place is write these into your spiral bound notebook. It takes a little more time, but I think it's not a bad idea to write these down and write them out longhand. It helps you to remember them better. So do that either way. A third option yet is do what I did, and that is I print these out and I write them by hand on my desk. That will require a lot of printing. It's going to be about 300 pages over the course of the 6 weeks or of this entire course. And so that's something, you may or may not want to do. That's what I prefer to do. I like to have copies of this. So do whichever one of those methods you choose. All right, so the two terms we have, if you want to write this out by hand here, are charge and conduction. Again, what we're really talking about is the force on electric charges, which would be protons and electrons, and how they eventually in this unit, how they interact with each other, the effect that they have on each other. So that's the very beginnings of studying electricity. All right, now we continue on with the instruction portion of the lesson.
We've just reviewed how charged particles behave when they get close to each other. One area of the study of charges is known as electrostatics. Static means stationary or having little motion or not changing. So electrostatics is the study of charged particles at rest. Usually when we see a thunderhead like this one in the picture, lightning isn't far away. This pretty yet threatening thunderhead is full of charged particles. We know that clouds are formed by condensing water in the atmosphere, but did you know that there is a negative charge on one side of the water molecule? Could this explanation be what causes the release of lightning? Before we can answer these questions, we should look at groups of charges and study interactions between them. What are charged particles, and is there a way to show the forces at work between them? When we speak about charged particles, we're referring to either subatomic particles or ions. Subatomic particles would include protons, neutrons, and electrons. An ion is an atom or molecule with a net charge due to a loss or gain of electrons. Here we have two examples. The hydrogen atom here has one electron that it easily gives away. That's because it's loosely bound on the first shell. And when it gives away its electron, it becomes a positively charged ion, as it now only has one proton. The second example is oxygen. It has 2 electrons on the first shell, making it stable, and 6 electrons in the second shell. But the second shell can hold 8, so oxygen tends to grab 2 extra electrons from somewhere. When it does, it becomes a negatively charged ion, because now it has 10 electrons, but only 8 protons. It takes a great deal of energy to separate an electron from its shell, so it requires powerful sources of energy. Heat is a form of energy, and 2 great sources for heat are stars and molten planet cores. A lot of the ions and free-floating electrons come from solar winds being pushed out of stars. In fact, there's 1 hydrogen atom in every 6 cubic meters of space. So Earth is picking up ions from space, but it can create ions as well from the molten core at the center of the Earth. You should also note that Earth, because of its size, can be considered a source of unlimited electrons and positively charged ions. In other words, the ground you're on is capable of both giving and receiving electrons.
All right, so as we look down below, we see a list of vocabulary words. There's a matching exercise, and that goes on to the second page of your guided notes. And again, you can write these out by hand, which is always a good idea. You don't have to literally write everything word for word, but be sure you know what each definition means and as many words as it takes to make that clear to you. So not all of these words appear right away. You're going to see these words throughout the lessons, throughout this entire lesson. All right, so let's move on to where we can do some answers based on what we just saw. And if you move on to page 3, there are some questions you can now answer. So an ion is an atom or molecule with a net charge. And this is due to the gain or loss of electrons. Why some atoms gain and why some atoms lose electrons is beyond the scope of this course. It's something that you will deal with in chemistry. Just understand that it does happen and that that flow of electrons, that movement of electrons, is called electricity. What we're dealing with in this unit primarily is non-moving electrons. It's just if an electron is just standing still, what kind of forces does it emanates from it? The same thing with a proton with a positive charge as well. Okay, down below, she mentioned a little bit about the sun and the earth. So two great sources for heat and are stars and molten planet cores. A lot of the ions and free-floating electrons come from solar winds being pushed out of stars. In fact, there's one hydrogen atom in every 6 cubic meters of space. Earth is picking up ions from space, but it can create ions as well from the molten core at the center of the Earth. Just a little bit of Earth and space science, not really relevant to electrostatics, but just a couple facts, because that's part of this class as well, is to learn about the Earth and space science as well. Okay, we'll continue on. All right, so next up is a question. An oxygen atom picks up 2 additional free-floating electrons. Is the charge on the newly formed oxygen ion positive, negative, or neutral? There you see the answer. Why is that? Because electrons are negatively charged. If you add 2 of them to anything, to any atom, that atom will have a more negative charge. So oxygen will become negatively charged when it picks up 2 additional electrons.
An electric field is the area around a charged object that can exert a force on other charged objects. Would we know an electric field if we saw one? Well, we can't see an electric field, but we can see places that you are likely to find one. In this picture, there are at least 2 probable locations of electric fields. The clouds are a good source of extra charges hanging around, so we could find electric fields there. And the plastic slide would be another good possibility. Have you ever gone down a plastic slide only to discover a wild hairdo when you got to the end? Well, your clothes rubbing along the plastic create charged particles through friction. For now, hold on to your electrons a little longer. We'll be talking about friction in a little bit. Now that we know what a field is and where we might find one, let's take a look inside at the forces in a field. An electric force is a force between 2 charged particles, ions, or objects. The electric force acting on a charged particle is determined from the charge of the particle and the magnitude of the electric field that it's in. This can be represented mathematically by the formula force equals charge times electric field. The electric charge is represented by a lowercase q and can be positive or negative. Electric field is represented by a capital E. The unit for charge is C for coulombs. And the units for an electric field are newtons per coulomb. When multiplied together, the coulombs cancel, leaving newtons for force, which is what we would expect. So we have force equals charge in coulombs times our electric field, which was newtons per coulomb. So you can see the coulombs cancel and we end up with newtons of force. This same formula can also be used to determine the strength of an electric field by rearranging to solve for E, or you can rearrange to solve for charge.
All right, so let's go ahead and answer these questions on page 3. An electric field is the area around a charged object that can exert a force on other charged objects. And there's some additional questions related to that particular panel. I'm simply referring to the boxes that you see that you move along during the lesson. Okay, so an electric force is a force between two charged particles. Those are called ions or objects. Q, electric charge, can be positive or negative. E is electric field. The SI units, that stands for System International. It's French. International system. It's really it's a name for the metric system. The SI unit for electric charge is the coulomb, which is abbreviated with a capital C. Simply the name of a scientist. When you see a formula, it's a good idea to do two things. Write out the units of measurement as they did on the video. So force is measured in newtons. That equals Q, which is measured in coulombs. I'm putting the unit of measure inside parentheses, times the electric field, which is measured in newtons per coulomb. The reason you want to get used to writing the units of measure is you'll see that if you have coulombs on the top in the numerator of a fraction here, if you only see one level on this, that means it's the numerator, it's the top, and you see it in the denominator here, that means they're going to cancel out. So when you multiply these together, the C's, the coulombs, will cancel. You'll be left with newtons, which is what's in your final answer. That's a very important technique to learn when solving problems, is this idea of unit cancellation. Over here, I'm going to write the formula out in words. You want to be sure that you understand intuitively what a formula means and that it's not just a formula, not just letters on a page. Okay, so force equals charge times the strength of the electric field. Okay, so I'm writing the formula in words, and the formula along with its units of measure. All right, the next question is a charge of 4.5 times 10 to the negative 5th coulombs is placed in an electric field with a strength of 2.0 times 10 to the 4th newtons per coulomb. What is the electric force acting on the charge? Okay, you can see the answer there. So how do we get that answer? Okay, so what I've done is I've written the two numbers involved, the charge and the electric field, and you always want to write the units of measure. Don't neglect writing those, because those will help you to line up the problem. If you weren't sure what to do with these two numbers, you know that coulombs has to cancel, and you want your final answer in newtons, and that's force. Those are the units of measure for force, just like they were back in Physics 1. Now, if you don't know scientific notation and you haven't watched, then you should go back and watch the scientific notation video that I put in this unit and also in the all videos section of the Google Classroom. But I've put that video here. Watch it. It's about 15 minutes, and it will teach you scientific notation. So how do we do that? Well, 4 times 4.5 times 2 is going to be 9.0. So you multiply the coefficients, these two numbers out in front, and you add the exponents. It's always going to be times 10. That never changes. So adding the exponents is negative 5 plus 4. If you need a calculator to do that, use it. That's going to give you negative 1. Usually when you answer a question in scientific notation, or when a question is given in scientific notation, you can leave the answer. But on the slide that we just left, they actually put it as a regular decimal number. So what does this negative 1 mean? It means you're going to move the decimal 1 position, and when it's a negative number, you move it to the left. You're going to make the number smaller. So that means you're going to move the decimal over here. So the way to write that as a regular decimal number is 0.9 newtons. Either one of these is an acceptable answer, 9 times 10 to the negative 1 or 0.9 newtons. So that is the answer to that question.
Every charged particle can be modeled as a sphere that exerts an invisible force field in all directions. To help us understand what we can't see, we use field lines to create diagrams of the invisible forces. When drawing a field diagram, there are certain rules to follow. Field lines always point away from or come out of the positively charged particles. And they always go into or point towards the negatively charged particles. Since the charges are spherical, when two particles interact, not all of the field lines have the strength to connect. The lines that are too far to connect will appear to go off into infinity. We know that two particles with the same charge will repel each other. So the field lines will not connect. They will bend when they're approaching one another. So the field lines show how these forces can physically push one object away from another. Two particles of opposite charge are attracted to each other, so the field lines between them would connect. The direction of the flow in the field is always from the positive to the negative. So don't forget to draw an arrow indicating the direction of flow when you're drawing a diagram.
All right, so the formal direction of the electric field is from positive to negative, but I want you to think about this. The things that are really going to be moving when we talk about electricity are the electrons. They're negatively charged. So which direction are they going to be moving? Are they going to be moving in the direction of the electric field from positive to negative, or opposite of the electric field from negative to positive? Well, the answer is a negative charge is going to be repelled by the negative, and it's going to be attracted to the positive. So electrons actually move in the opposite direction of those field lines that you see right there. And so they are the objects that are actually going to be moving when we talk about electricity. All right, so here's a simple question. It says use the drop-down menu to complete the statement based on the field lines. The electric charges indicated by the question marks are they the same or are they different? Well, those lines are indicating that they are repelling each other. You don't see lines going from one of the particles to the other. That would be attracting. So you don't know whether they're both negative or both positive, but they're both the same.
You've been doing a great job answering the lesson question, how do electric charges behave? We've learned a charged particle forms a field that can exert a force on other charged particles. Now, just because we mentioned a field and applying forces to one another does not mean that this is a play diagram for football. This is a drawing of two charged particles moving in an electric field. The X's represent an electric field moving from your chair into the screen. A positive charge could be a positive ion or a free-floating proton, and a negative charge could be a negative ion or a free-floating electron. The forces applied to these two particles once they enter the field alters their course, and they bend. Before you learn how electric forces can affect electric potential energy, take a moment to learn a few more words that will be used in the rest of the lesson.
So I'm not sure I don't think that this diagram is drawn correctly. And you should understand this, the symbolism that they're using here. If you think of a bow and arrow, somebody shoots an arrow, the front of the arrow has a tip on it, and the back of the arrow has feathers on it to kind of guide it. They act kind of like the tail on an airplane to keep it going straight. So if you imagine an arrow going away from you, you're going to see those feathers on the back. And that's what this symbol is, this X's, the X's. They're like the back of an arrow. So this is an arrow that's moving away from you. If they were to show dots there, that would be an arrow that's moving out of the screen towards you. So that's the symbolism that they use. So if you remember that the electric field moves from positive to negative, think of your head as being positively charged, and think of something behind your computer screen as being negatively charged. Then that would be the proper direction for these electric field lines. They would be moving from positive, your head, to the object behind your computer screen, directly behind your computer screen, which is negatively charged, and therefore you would be seeing the back of these electric field lines, and you would be seeing those X's. If that's the case, then if you put a positive charge in that electric field, it's going to move from positive to negative. In other words, it's going to move away from your head and towards that object in back of your computer screen. So that positive charge really isn't bending up the way they show there. It's really going through your computer screen to that negatively charged object in the back. Similarly, the negative charge there is going to be moving away from the negative charge and towards the positive charge, which is your head. So it's going to be coming out of the computer screen, and it's going to fly out and hit you in the head. The negative charge will. So positive charge will be moving away from you. Negative charge will be moving towards you.
Be sure to type these 6 important science vocabulary words as you move through the lesson. Be sure to type these 6 important science vocabulary words into your e-notes and check your glossary for definitions. Stay on the lookout for these vocabulary words as you move through the lesson. Conduction, conductor, electric potential energy, induction, and insulator. The potential energy an electric charge has due to its location in an electric field is known as electric potential energy. And most of the time, PE is used for potential energy. But now we're using a capital E to represent electric field, so the electric potential energy of a charged particle will be represented by a capital U to avoid confusion. The electric potential energy of a particle can be represented mathematically by multiplying the electric force exerted on the charged particle by the distance between the particle and the source of the electric field. Remember, electric force is just charge times electric field, so it could also be written U equals QED. Now the unit for electric potential energy is the joule, and this makes sense because force is in newtons, distance is in meters, and 1 Newton meter is the joule.
All right, so we'll keep a running formula sheet for this particular unit. So we have force in newtons equals charge times electric field. the formula that was just given in the last lesson or last panel was potential electric energy, and that's equal to force times distance. If you remember from Physics 1, work equals force times distance, but work and energy are really effectively the same thing. They're kind of two sides of the same coin because they're both measured in joules. So in this case, we can say that potential energy is equal to the force times the distance that over which the electric field is spread. And then finally, they can expand that out since force equals Q times E, that potential energy equals Q times E, that's force, times distance. All right, so we're given a problem here. A charge of 4.5 times 10 to the negative fifth coulombs is placed in an electric field with a strength of 2.0 times 10 to the fourth newtons per coulomb. If the charge is 0.03 meters from the source of the electric field, what is the electric potential energy of the charge? Okay, and you can see the answer there, but how did they get that? So let's go ahead and work that problem. All right, so this is how you would set up this problem. This is the charge value that they gave you. This is the electric field in newtons per coulomb, and this is the distance in meters. So coulombs cancels. Coulombs cancels, and you end up with the units of Newton times meter, and that's a unit of work or energy. So now let's do the math on this. One thing I did not show you in the scientific notation video is what do you do if you have scientific notation numbers and then one that's not a scientific notation number, and you really treat this just as a coefficient and you multiply this by this by this. Just to show you, this number could be written as 0.30 times 10 to the 0th power. Remember, 10 to the 0th power is not 0, it's 1. So 1 times this equals this. So you could write it in scientific notation, but there's no need to do that. So we're going to multiply this times this times this, and that's going to give us 0.27. And now we do go ahead and add the exponents again like we did before, and just as with the last problem we get to the negative 1. So you can leave the answer like this. Well, you can't really. You'd have to move this over to there, make that number bigger, make this number smaller. But the way they presented the answer, well, let me show you that. If you wanted to leave this in scientific notation, you may have to make this a number between 1 and 10. So that's going to equal 2.7. And remember, the reasoning from the video that I made is if you make this number bigger, you have to make that number smaller because you don't want to change the value of the number. So that's times 10 to the minus 2. That's one way to write that. The way they do is they go ahead and convert it to a regular decimal number. So if you have this number, to the minus 2, you move the decimal 2 places to the right, or excuse me, to the left, and you fill that in with a 0. So the answer is going to be 0.27. Remember, this 0 is meaningless. It's just something that they put in front of the decimal, but that would be the actual answer that you would get from this number if you express it as a decimal.
The electric potential of a charged particle can be determined by dividing the electric potential energy by its charge. So the electric potential of a charged particle can be represented mathematically using this formula, where V is the electric potential, U is the electrical potential energy, and Q is the electric charge. The unit of electric potential is V for volts, which is equal to joules, which are the units of electric potential energy, over coulomb, which is the unit for charge.
Okay, so we've added another formula here, which is that electric potential, which is known as voltage, is equal to the potential energy divided by the charge. I find that formula a little more useful to move the Q over to the other side and say that electric potential energy equals electric potential times charge. You can think of electric potential as kind of like the gravitational field. So if you want to know how much energy you have a bowling ball. If you want to know how much energy it's going to hit the ground with, it's the gravitational potential times the mass of the bowling ball. If you get a more massive bowling ball in a gravitational field, then it will hit the ground with more energy. So V is like gravity, and Q is like the mass of the bowling ball, except in electricity, it's not the mass or how heavy the object is, but it's how much charge that it has on it. All right, let's go on. All right, so for our next problem, we have what is the electric potential? So that's voltage, and you can see the unit of measure they give you with the answer is V, of a 4.5 times 10 to the negative 5 coulomb charge that has an electric potential energy of 0.027 joules. So we'll go ahead and write out the formula and go ahead and solve that. Okay, so there's our problem. Let's go ahead and bring up a piece of paper to write that on. All right, so we have V equals potential energy over charge, which is, let's check that out. Let's go back here. Okay, 4.5 times 10 to the minus 5, excuse me, it's 0.027, that's the potential energy. Joules is the measure of energy, divided by 4.5 times 10 to the negative 5. So I'm going to go ahead and write that down. Okay, and there we have, I wrote it right there. So now again, you have a little math problem to do here with scientific notation. So you simply divide this number by this number. Okay. And you're going to learn a little trick of scientific notation. Okay, and what that gives us is 0.06. Okay, now what do you do with this? If you ever have a number, any number, not just scientific notation, with an exponent on the denominator, you can move it up to the top and you change the negative to a positive. Okay, I'm not going to go into the math of why that is right now. We're just going to do it. Just learn the principle. So that becomes 10 to the 5th. Okay, and I made a mistake here. I omitted a 0 here. There should be another 0 here. So let me correct that. So it's 0.006 times 10 to the 5th. So let me go ahead and correct this. We're going to do the same thing. I just needed to add another 0 there. Okay, so we're going to move it 1, 2, 3, 4, 5. There's the decimal. You fill these in with zeros. Once you move the decimal there, these just go away, these leading zeros. So your answer is 600. And the units of measure for voltage is volts. So that is your answer, okay? So doing some of this math will take a little bit of getting used to, but that's okay.
Charged particles can move or flow depending on the type of material holding the charges. A conductor is a material that allows electricity or thermal energy to easily flow through it. Charges flow when free electrons, that is, electrons that are no longer attached to atoms, are readily available in the material. The higher the number of free electrons, the greater the conductivity. Most metals have free electrons, so most conductors are made out of metal. On the periodic table, if you draw a line right about here, everything to the left of that line is a metal. Other good conductors include water, and any solution that contains ions. An insulator is a material that restricts the flow of electricity or thermal energy. If you're guessing that insulators are materials without free electrons, you would be absolutely right. Why do you think this cat is on the cushion? Maybe it's because the floor was cold, and these cushions are insulators keeping the cat warm. Other examples of great insulators are rubber, glass, and wood.
All right, let's go ahead and get caught up with some of our guided notes here. So charges that are the same blank each other, that is repel. They're the same, they repel. That was a few panels back. Charges that are different, blank, that's attract. So as you'll see that these questions are not necessarily in the order that you see them in the video sometimes. Okay, let's go ahead and move on. Let's answer a few more. Okay, down here. These two were in panel number 6. So field lines in the diagram indicate the direction of the flow of the electric field between charged particles. Point blank from positively charged particles. So the electric field points away from positive and towards negative. All right, and down here, force exerted by charged particles. When two charged particles come near each other, the electric fields of both objects are charged. When like charges are near each other, the field lines bend away. And when unlike charges are near each other, the field lines combine. Okay, now moving on to page 5 of the guided notes. Electric potential energy is the potential energy an electric charge has due to its location in the electric field. And there you see the formula for potential energy. Electric potential, don't get the two confused. Potential energy is measured in joules. Electric potential is another word for voltage. So you need the potential energy divided by the charge to get the voltage, or the voltage times the charge gives you the potential energy. In other words, potential energy, what you're really interested in anything in physics, is energy. How much energy do you get out of something? And if you take the voltage, that's how much push is being put on the electrons, times the number of electrons, that's the charge, that'll tell you how much energy you're going to get out of electricity. So electric potential is electrical potential energy of a charge divided by its electric potential energy of a charged particle divided by its charge. All right, and this last panel she talked about conductors. A conductor is any material that allows electricity. Just think of a copper wire that conducts. You easily move through it. Metals, water, and ionic solutions. And I'm going to write not really here. Water, pure water, is not a conductor, although they say it is in the video. It does not have free electrons that can easily move through the water. The reason water is thought of as being a conductor, or that you can get electrocuted if you stand in water and there's an electric wire, is because there are ions there. There are metals and other things that can produce electrons. But pure water is not a good conductor, actually. But they say it is, so, I'm just letting you know that. All right. And an insulator is a material that restricts the flow of electricity or thermal energy. And things like that would be rubber, glass, wood. So a power cord coming from your computer into the wall has got conducting metal inside of it, but it's surrounded by rubber insulator to keep you from shocking yourself. Okay, so the next panel has some questions. Classify each substance as either conductor or insulator. A sample of mercury. Mercury is a metal. So even though it's liquid at room temperature, it's one of only 2 elements on the periodic table that are liquid at room temperature. It is a metal, and so it's a conductor. Glass, you can't get shocked through a piece of glass. Glass does not have free electrons to move about and create electricity. A rubber hose, rubber does not conduct electricity. And negatively ionized lithium paste, just the key words are there as ionized, and so that is a conductor.
By now we know what charges are, the forces they place on each other, and the fields they're in. But how do they move around? Take a look at this situation the poor cat got himself into. His curiosity about those packing peanuts got the best of him. Let's look at 3 ways that charges can move and try to explain things like these peanuts sticking to the cat. These 3 ways charges can move are friction, conduction, and induction. In order for charges to build up, charges have to move from one place to another. And there are 3 ways that this can happen. The first way is a result of friction. In charging by friction, electrons transfer from one object to another when the objects rub against each other. So if you rub a glass rod with a piece of silk fabric, electrons move from the glass rod to the silk fabric. Since the glass rod loses electrons, it becomes positively charged. And the silk fabric gains electrons, so it becomes negatively charged. The cat covered in packing peanuts was a victim of friction. The cat's hair rubbing against the peanuts caused electrons to be transferred and made the packing peanuts sticky. The second way in which electron charges are transferred is by conduction. Conduction occurs when electrons are transferred from one object to another by direct contact. In the first example, a negatively charged rod is brought into contact with a neutral sphere. Electrons move from the rod to the sphere, and the sphere becomes negatively charged. In the second example, positively charged rod is brought into contact with a neutral sphere. Electrons move from the sphere to the rod, and the sphere becomes positively charged. In both examples, the end result is that both objects will have the same charge. In the first example, the negatively charged rod causes the sphere to become negatively charged because of the contact. In the second example, the positive rod causes the sphere to become positively charged because of the contact. It's important to know that only electrons move to create a positive or negative charge. Positively charged protons do not move to create a charge. Negative charges result from an excess of electrons, and positive charges result from a depletion of electrons. The third way in which charges are transferred is induction. Induction occurs when electric charges are transferred without direct contact. At the start, we have 2 spheres, A and B, and they have no charge. In this middle picture, a positively charged rod is placed near, but not touching, sphere A, and it attracts the electrons, which are negatively charged. So the electrons move to the left sphere because of this attraction, leaving the right sphere depleted of electrons and thus positively charged. Then when sphere A and sphere B are separated, Sphere A is negatively charged and sphere B is positively charged. So do you remember our ominous thunderhead? Clouds collect extra electrons, causing them to become negatively ionized, similar to our positively ionized glass rod here. When a thunderhead moves over land, the land becomes positively ionized by induction. At some point, the two ionized paths connect and the charges are released through the static discharge, or what we call lightning.
All right, so 3 ways that electrons can move, and it is only the electrons that move, is by friction. For example, rubbing a glass rod with a cloth, and that will cause a transfer of electrons. That's not real common. I mean, it's common in everyday life. You drag your socks along a carpet and you touch a doorknob and you've got electrons all over you. It's going to discharge. The other way is conduction. That's the most common. That's where you have a direct connection between the positive and the negative ends of the electric field, and the electrons can flow through a wire. And then there's induction, the last one that she talked about. An example of that, think of an electric fan. How does an electric fan turn? You know the electricity comes out of the wall and into the fan, but the motion part, it can't have wires connected to it, or they would spin around and around and around, those wires would, and they'd wrap up and they'd stop the fan. So somehow it has to have a way to transfer electricity from the part of the fan that's not moving, and that's called the stator, to the part of the fan that is moving, and that's called the rotor. And that's a relationship between electricity and magnetism that causes that to happen. But the point to be made here, we'll get into that later, but the point to be made here is that the electricity coming from the wall is creating an induction effect in the part of the fan that turns. There aren't electrons directly flowing from the wall into the turning part of the fan. I mean, how would they get there? You don't have any wires there. So they do it without touching, and that's called induction. All right, so here's an exercise to just identify these 3 methods of moving electrons. Match each method of transferring electric charge with the correct description. So induction. You can see the answers there. That's the transfer of electric charge without direct contact. That's the key phrase. Without direct contact is induction. Friction. That's the transfer of electric charge by rubbing. And conduction. That's the transfer of electric charge by direct contact. So that would be electricity moving through a wire. Wire connecting the positive and negative terminals to allow the electrons to flow directly. All right, and they give you a little exercise here. So they say a yellow balloon has a positive charge and the blue wall has a neutral charge. But neutral doesn't mean it doesn't have electrons and protons. It does. It's just they're neutral. There's an even number of them. So that's what neutral charge means. But it does have protons and electrons. Everything does, because everything's made out of atoms. It says press proceed to move the balloon closer to the wall. Okay, so we'll do that. Now, click or tap the section of the wall that will be induced with a negative charge. So would it be the right-hand side? Would they be spread out evenly? Or would it be the left-hand side? Where are the negative charges going to suddenly move to? And the answer would be right there, to the left-hand side. They're going to be attracted to the positive charge. Okay, so this concludes the lesson of both the warm-up and the instruction. I'll do a different video for the assignment, and then I will give you a quiz review on that. That'll be up later on Friday, June the 26th.